Section 2.7 deals with the limit of a function. We've done a little bit of work with limits. We're going to look at some other applications of that today. So using limits to define the continuity of a function at a point. So the function f has a limit L at x equals a, some value for x, written like this. The limit as x approaches a of f of x equals L. So this function has a limit if we can make the outputs, or the function value, as close to L, an output or y value, as we wish, by taking the inputs x sufficiently close to a, but not equal to a. Remember when we talked about our limit as h approaches 0, we didn't really care about what happened when we got to 0, just what happened when we got really, really close. So the same thing applies here. Okay, so for example, if we have a function, and it looks like this, and we want to know the limit at x equals a, so we go up to that, and our limit is the output value. So the limit is a function value. The place where we are finding the limit is an x value. So find the limit of x squared minus 9 over x minus 3. In other words, what happens to the function as x gets really close to 3, but not equal to 3? In this case, if x is 3, if we plug in 3, we would get 9 minus 9 over 3 minus 3, which is an undefined or indeterminate value. We can't do that. But what happens really close to 3? Well, get out your calculators and go to y sub 1, and let's put in this function, not with the limit, just the function itself. So you're going to need a parentheses, x squared minus 9, divided by, and another parentheses for the denominator. So take a minute and put that into your calculator under y sub 1. Okay, now we're going to go to our table feature. And if your table is not already on a function or a mode that allows you to put in whatever value you want, go to Second, Window, and you will see something that says Table Start or Table Setup. So what I want you to go do is to go down to where it says Independent, Independent, and change that from Auto to Ask. Put your cursor on Ask and highlight it and push Enter. Now, go to your table. Under the table, I want you to enter these values. I want you to enter X, and then you're going to get your Y sub 1 values. So I want you to put in 2, 2.5, 2.9. We're getting closer and closer to 3. Let's go ahead and get really close, 2.999, and then put in 3. So if you set up your equation right in your table correctly, we will get 5, 5.5, 5.9, 5.99, 5.999, and then you'll get an error message at 3, because as we said, we can't plug 3 into this function. Let's see what happens if we keep going. Let's do 3.001, 3.01, 3.1. We'll go ahead and do 3.5 and 4. So 3.001 gives us 6.001, then 6.01, 6.1, 6.5, and 7. So as we're approaching 3 from both sides, we are getting closer and closer to 6. So we can say that the limit as x approaches 3 of x squared minus 9 over x minus 3 equals 6. Even though the function value doesn't exist there, we can find a limit, because limits are about what happens as we get really close but not equal to. So we just found out that limits can exist even if the function value does not exist. Now sometimes as we approach a particular limit, we are going to get different values from each side. Limits from the left and from the right may be different. These are called one-sided limits. So let's take a look at how this works. So here's a lovely function. Do a quick sketch of this. Get some of these critical points on your graph that are labeled here. I'll let you take a minute and copy this down. It doesn't have to be exact. Okay, let's look at the limit as x approaches 0 of this function, which we're going to call f of x. So as I get closer to 0, and I'm going to need to change color because that yellow is not going to show up on the okay, so as I get closer to 0 from both sides, so coming from the left close to 0 and then from the right close to 0, my function value goes towards 1. So the limit as x approaches 0 of f of x is 1. Remember, the limit is my y value. Let's look at the limit as x approaches 3 of f of x. So again, as I get closer to 3 from the left and the right, we are getting closer and closer to 0. Now, the function value does not equal 0. As a matter of fact, f of 3 is -1. So you can see that the limit is 0, because as I get closer and closer, I am approaching a 0 value for y. I don't care what happens when I get to 3. That's my function value. My limit stays at 0. Try a different color again. These colors are not showing up on both the dark and the light. Let's try this one. All right, now what about the limit as x approaches -2? So this time, as I approach -2 from the right-hand side, coming closer this way, and then as I approach -2 from the left, the function is going to two different places. So let's look at two separate limits, the left hand and right hand. So my left hand limit is the limit as x approaches -2 from the left, from this side of the graph, coming this way. And as I approach -2 from the left, the limit of f of x, coming from the left, I'm following my graph left to right, is 2. My right-hand limit, written as the limit as x, come on, go back, the limit as x approaches -2 from the right of f of x, coming from this side and moving this way, coming from the right, when I get close to -2, I am close to -1. So my left-hand limit is 2. My right-hand limit is -1. So the limit as we approach -2 does not exist. There is no limit, because if the limit means approaching from both sides, there is no place that the graph is going to. It's going to two different places. However, the left-hand limit can be found and the right-hand limit can be found. We'll do a couple more of these in class. That's left-hand and right-hand limits. Sometimes they are the same, as they are at x equals 0 or x equals 3, and therefore we can say that there is a limit. Sometimes we have a left-hand limit and a right-hand limit, but no limit. One-sided limits, here's our definition. The right-hand limit, written as the limit as x approaches a from the right of f of x equals L, means that f of x can be made as close to L as we wish by taking x sufficiently close to a, but a little bit greater than a. In other words, coming from this side, if this is a, we want to use values just a little bit greater than a. The left-hand limit is the limit as x approaches a from the left of f of x equals L means that f of x can be made as close to L, the function value can get close to the y value, as close to L as we wish by taking x sufficiently close to a but less than a. So in this case, we're coming much closer, but a teeny bit less than a. So that's our right-hand limit and our left-hand limit. So let's talk a little bit more about our limits and how we've been using them. One of the ways we've been using it is finding the limit of secant slopes gives us the slope of the tangent line. So this is two ways to write it. The limit as h approaches 0 of my y sub 2 minus y sub 1 over x sub 2 minus x sub 1, that's just a slope of the secant line, limit as h approaches 0, or between 2 points, the limit as x approaches a of f of a minus f of x over a minus x. Same exact thing with a different notation. In this case, we have a value x and a value x plus h, and we are making h approach 0. This one, we have a value a and a value x, and we are having x approach a. It means the same thing. It means we're taking our secant slope and bringing it closer and closer until we were right on top of the original value. So we've already done this. We've done it a couple of different ways, but this is another way to use a limit. Okay, rules for calculating limits. If the limit as x approaches a of f of x equals L, and the limit of as x approaches a of g of x equals m, and if k is a constant, then we can follow these rules. The sum rule. The limit as x approaches a of the sum of the functions is the sum of the limits. So if I add two functions together, but I know their limits individually, I can just add their limits up. Difference rule, same thing, but with a subtraction sign. Product rule, same thing with a multiplication sign. Pause and write these down. The quotient rule, same thing, but with a division sign, and we have to make sure that m does not equal 0 for this to work. And the last one, if the limit of a function is multiplied by a constant, then the limit is also multiplied by that constant. Okay, let's look at a couple of these rules. I've got two graphs here. I'm going to call this one f of x and this one g of x. So what would be the limit as x approaches 0 of f of x plus g of x? Well, let's look at the limit as x approaches 0 of f of x and add that to the limit as x approaches 0 of g of x. So see if you can figure out what the limit is for f of x, the top graph, as we approach 0. So hopefully you saw that as I came towards 0 from either side, I was approaching -4. And then on this graph, as I approach 0 from both sides, I approach 0. So -4 plus 0 equals -4. Okay, let's look at the limit as x approaches 2 of, let's do f of x times g of x. So the first thing I need to find is the limit as x approaches 2 of f of x, and then I'm going to multiply that by the limit as x approaches 2 of g of x. So see if you can find those two limits. So as I approach 2 on this graph, my limit is 0. As I approach 2 on this graph, even though there's no value there, my limit is -2. Multiplying those together, I get 0. What happens if I want the limit as x approaches 1 of f of x minus g of x. Well, I have a problem here because the limit as x approaches 1 of f of x does not exist. As I approach 1 from the left, I'm approaching what looks like about 1/2. As I'm approaching 1 from the right, I'm approaching -3. There is no limit. This does not exist. Therefore, the limit of the difference does not exist. Okay, one more piece to look at. If the function is continuous and has a function value at x equals a, then the limit can be found by simple substitution. Let's look at a function like f of x equals 3x minus 1. Well, we all know that that is a simple line that goes through -1, has a slope of up 3 to the right 1. It's a straight line. It doesn't have any breaks or gaps. So if I want the limit as x approaches 1 of f of x, which since I know the function, let's write it with the function in there. From the graph, it looks like that is at the point 1, 2, so it looks like the limit should be 2. Let's try substitution. So that is the limit. It's also the function value. So if you can substitute a number into an equation and get a value, that is also the limit. So let's look at this. F of x equals x cubed minus 3x plus 1. Let's find the limit as x approaches 2 of this function. Let's just try plugging in 2 and see what we get, which is 8 minus 6 plus 1, which is 3. So this limit is 3. If I were to graph this, it's a cubic function, but at 2, the function would go through 3, looks something like this, and that is my limit. So if the function doesn't have a hole in it or anything else, then our function value is also the limit value. Let's go back to that very first function we looked at. And we already said that if I want the limit as x approaches 3 of this function, I cannot plug in 3 because I get an undefined. So we used a table of values. But let's look what happens if I simplify this by factoring. The x minus 3's will cancel, and this equals the limit as x approaches 3 of x plus 3. And now I can plug in 3, and I will get 6, which is what I got from the table. Now, the important thing to keep in mind here, if you still have that function in your calculator, I want you to graph it and see what it looks like. So if you still have that function in that says y equals x squared minus 9 over x minus 3, take a minute. Gotta get my calculator working again. And go to a graph. So what the graph looks like is this line, y equals x plus 3. It looks exactly like this. This function and this function are identical except at the value where x is 3. My second function, my simplified function, is a solid line. I can plug in my limit value to find my limit. My original function has a hole here at 3. You can't see it on the graph, but at x equals 3, there is a hole, which was why I could not plug it in back here. However, the limit of the graph with the hole is exactly the same as the graph without the hole. So when we're talking about limits, if I simplify, I can sometimes plug in my value to find my limit. So that's it for this, and I'll see you in class.